Okay, we're going to continue on here. We've been talking chapter 14, and we talked about a couple more organic groups, our carboxylic acid, which once again has the functional group of carbon oxygen double bond 2 and OH. And again, sometimes that's written as COOH in sort of formulas. Um, and remember that when we name carboxylic acids, we sort of end it with oic acid. It again is based on the longest number of carbons in the chain that obviously contains this functional group here. Just like we talked about with aldehydes, because this functional group does have this hydrogen at the end, this functional group will always find this spot located at one end or the other. And because of that, we don't have to give the number exactly where that carbonyl carbon is, the carbon oxygen double bond, but always for numbering purposes for other groups that are there, that should always be your carbon number one, whichever sort of side it is at. And then you can number your other groups accordingly. We again can form a carboxylic acid, as we talked about, really from way back where the oxidation of a primary alcohol to an aldehyde, and then one more oxidation again gets us to our carboxylic acid along the way, or just obviously if you're starting with an aldehyde, just oxidize a aldehyde. The other group we talked about was the ester group, and the ester group is very similar to the carboxylic acid. It has the carbon oxygen double bond. It does have the oxygen, but here it is going to be connected to really another carbon. It doesn't have the H at the end. So again, here we will see this group inside, not really at the end. And this is made through, as we were talking about at the end there, an esterification reaction. And it is a reaction between a carboxylic acid and an alcohol. And so that reaction between a carboxylic acid and an alcohol, you basically just kind of remove water. Here, I'll put a CH3 there, and we'll just pop a CH3 right there. And once we remove water, we basically just kind of squish everybody together so that we do get this connection that's important. That's always the connecting point. So we got CH3, C double bond O, and then obviously here we're going to go to our O and then to our CH3 in this case. And that gives us, again, our ester bond. That is the formation there from our alcohol and our carboxylic acid. And once again, it is basically the removal there of water to do that. When we go to name these, as we were talking about before at the end last time, really perhaps the easiest way to do it is just to kind of put a line between that connection. And there's really, again, two parts to this ester. There's obviously the carboxylic acid part and there's the alcohol part. So as you go towards the carbon oxygen double bond, that's always, as you can see here, obviously in our carboxylic acid, that's in the carboxylic acid. So that's the carboxylic acid part. That also is going to be the main part of the name or the base part of the name. And in this case, there's one and two carbons. So two carbons is ethane. And the way that we name esters is we actually put O8 at the end of it. So that's going to be ethanoate for the carboxylic acid part. Remember, if you kind of go away from the carbon oxygen double bond to the single oxygen, that's going to be your alcohol part of the compound. And remember, the alcohol is really just going to be kind of named as a group. And in this case, we would have just a one carbon group, and that's going to be a methyl. And we would end up with something like methyl ethanoate. So again, here, OAT is how we sort of name those esters. Again, this is through this esterification reaction. Just basically take water out and then just kind of squish everybody together. As I might have mentioned last time, if you have to draw this or you have the structures, it's sometimes helpful just to back up and draw them. So you have kind of the hydrogens facing each other, and then you can kind of just put a box around the water and then just copy everything and squish them together without the water, and then you'll end up with the right sort of structure. So that's a good way to kind of arrange it if you needed to draw it. And maybe this alcohol, and in a lot of cases, alcohol probably won't be necessarily facing the hydrogen like that. It'll just be like the alcohol given to you. So just redrawing it like that sometimes very easy. Any questions on that stuff there? All right, continuing on there. So why don't we do this one? Let's write the balanced equation for the reaction of propanoic acid with methanol with heat and an acid catalyst. So it's good practice drawing all those guys. So why don't we draw the structures of all that and then draw what you get. So we're going to take propanoic acid, we're going to add it to methanol. Okay, let's take a look. So once again, since we need to draw these structures, always want to work backwards. So we'll start with the first one here. So we're going to go this way. We see oic acid, which should tell us is a carboxylic acid. And obviously the propane part tells us is 3 carbons. So we'll start with that, 3 carbons. And because it's a carboxylic acid, you will have the carboxylic acid functional group on there. You can put it on either side, but I'm going to put it over here. And now I'm just going to, again, fill in my hydrogen. So I do need 2 there, and I do need 3 there. So that's propanoic acid. We have methanol, that's OL, which tells us it's an alcohol, and it has an OH group on it. And methane basically is 1 carbon. So that's going to be carbon with an OH, and obviously I'm going to fill in my hydrogens in this case, and it's going to look something like that there. Any questions on those 2 there? All right, at this point, this is a carboxylic acid. This is an alcohol. This is going to make an ester over here, which means we're going to take water out. So as I was mentioning a second ago, you may just want to redraw maybe your alcohol or one of those so that the H's back up to each other. So I'm going to re-erase this here. And again, just kind of turn it around. So orientation wise, it is going to be much maybe easier to kind of figure out my end product here. Again, you just want to have the H's kind of pointing at each other basically. And at that point, all you have to remember is we're just going to take water out. So however you want to take water, it really doesn't matter. I'm just going to box 2 H's and an oxygen. And obviously that part's going to come out, and the rest you're just going to squeeze together basically. And now you can basically just copy, start left to right there and just copy what it's up there. So I got a CH3, I got a CH2, I got a carbon with a double bonded oxygen there. I got me an oxygen. Obviously, I'm going to take the water out, so I'm not going to copy anything that's in the box. I'm going to pick back up here on my alcohol side, and we're going to do a CH3 there. And if you want to be all fancy with it, you can't put the water there as well. But the main thing there is our ester, which we could see right here is our functional group. Yeah. Any questions on that one there? We could also name this, again, same deal. We're just going to kind of put a line between always the single bonded carbon and the oxygen. So once again, the base of our name is going to come from the carboxylic acid side, and that is again 3 carbons, as we know from our propanoic acid. So that's going to be propanoate. Going the other way is our alcohol, and that's going to again be named as a group, and that's going to be a 1 carbon group, which is a methyl. So we got a little methyl propanoate in this case. Yeah. Any questions on that there? So like I was saying before, that's sometimes an easier move. Just kind of get those H's lined up, box out the water, and then just put them together. Yes. Does it matter the naming? Is that what you're asking? It doesn't matter in the sense that the carboxylic acid part should always be kind of the base of the name, the end part. And then the alcohol part should always be named in the front as a group. So it should always come kind of alcohol part first and then carboxylic acid part at the end in terms of the naming. Yeah. Other questions? Yeah. All right. And they drew the same thing, which is good. That's good. All right, so as we've been sort of obviously talking about as we've been going through this, again, through this esterification reaction, we're going to make the ester. And again, those are the 2 parts that you need to kind of look at when you want to name it. And as was sort of a question the other day, you can always, like I said, just just put a line right there, and then that will always sort of give you your sort of parts that you need for the name. Always between the carbon oxygen single bond. And again, towards the single bond, just like it is in the alcohol part, it's all single bonded. That's the alcohol part. The part with the carbon oxygen double bond heading that way is always going to come from the carboxylic acid part. So you always sort of have your parts sort of organized in that sense. And I think that's the one we just did there. So methyl, that's also methyl ethanoate. All right. Now, esters do have common names. We're not going to really use common names for esters. We are going to use the IUPAC way of naming, which is what we've been doing. So once again, just looking at each of these and running through the names, like we kind of did some of these examples. Again, here, we could put our line there. Towards the single bond is the alcohol. And again, towards the double bonds, carboxylic acid. We start with the carboxylic acid. That is 2 carbons, hence the ethane part. And we put the O8 at the end of that. And here we actually have 2 carbons there for the alcohol part. And again, that is where the ethyl part comes from. So ethyl ethanoate. Um, coming to the one next to it, again, same idea. I'm just going to put my line right there. Again, towards the double bonded oxygen, carboxylic acid, towards the single bonded oxygen, our alcohol. And once again, we have 3 carbons there, which is going to give us propanoate. And again, our 1 carbon, which is going to give us our methyl. I think we mentioned this last time in these examples. Obviously, the carbon oxygen double bonds to the left there, but it can be on the right. So I think we did one the other day where it is kind of on the right. So again, you just want to think about going towards the carbon oxygen double bond for the carboxylic acid side. Over here, we're going to do kind of the same thing here. And here we have, this is going to be our carboxylic acid side, and this is going to be our alcohol. Now, this one is a little bit maybe different, but this is a benzene ring, and that's going to give us benzoate. Now, you may be saying, isn't there an extra carbon kind of hanging off of the ring there? And remember, though, with the benzoic acid, which is where that part comes from, the benzene ring is the main part, and the carboxylic acid group is hanging off. So that is why when we kind of lose the water, when we put it with the alcohol on this side, we do still have that extra kind of carbon hanging off there, and that's why it's not incorporated into the name, because this entire thing here is carboxylic benzoic acid, and that is where obviously the benzoate comes from. And remember, it's not part of the ring because of the triple bond, or not triple bond, but the 3 double bonds that are present. Coming the other way, we have our 2 carbon group, which is our ethyl. So a reminder, as we talked about last time, again, you could have something that looks like this. So it really doesn't matter sort of which side that carbon oxygen double bond's at. We're still just going to draw a line between, again, that carbon oxygen single bond. Now, in this case, we actually want to go this way, as that's going to be my carboxylic acid part to the right. And this part with the single bonded is going to be my alcohol. So again, 1, 2, 3, 4 there. So that's going to give us a butanoate. And our alcohol part there has 2, which is going to be an ethyl. So again, not always will the carbon oxygen double bond be there on the left. It could be on the right or the left. But that's where you want to focus in on, is on that functional group. And again, just draw that vertical line between the carbon oxygen single bond that's next to it. And then that will kind of orientate which way you need to go to get to both parts of it. Any questions on that there? As I mentioned before, a lot of esters in the last lecture. Again, it's a lot of things that has aromas and certain tastes. Also, aspirin is an ester as well. So you can see there, salicylic acid, we have our ester group happening right about there. Why don't you give this guy a name here? See what you come up with. About there. Going to do my vertical line right about there, again, between the carbon oxygen single bond And towards the double bond carboxylic acid side, can give me the base of the name. Once again, 3 there is going to be based off of propane, propanoate, O8 at the end of it. And coming the other way, which is our alcohol part towards the single bond, we got again our 2 carbons. So once again here, ethyl propanoate. Yeah. Any questions on that one there? All right. All right. Now, as I mentioned, esters in fruits. Actually, here, let's go back. I skip one there. All right. Why don't you give the name of this? Why don't you also maybe, why don't you draw some here? Why don't we draw, let's do propyl hexanoate. And why don't you draw butyl. And I would say probably if I was going to draw these, I would actually start with the functional group first and then kind of put everything else there. Just kind of orientates everything in a better way, maybe, than trying to kind of put everything together. So what I know for the functional group is this, and it's really just the part of the ester where we kind of split it off anyways when we're naming. So I would actually start with just the carbon oxygen connection there. And that's where we normally put our vertical line, right, to figure out which side is our carboxylic acid part and which side is our alcohol part, right? So that's a good kind of starting place when you're drawing these. And I would do actually the same thing, right? So I'll put the line here, but obviously in our structure, we don't need the line. But obviously, if I were going to name this and I had this functional group there, again, heading in this direction should be my carboxylic acid part, and heading in this direction should be my alcohol part. And by the way, since you're drawing it, you could put the single bonded oxygen facing the other way if you wanted to. It's all good, whichever way you want to draw it. Now I really got kind of a foundation, so I'm going to get sort of my functional group correct here, hopefully, without trying to just maybe do all the carbons and then try to figure out how to kind of fit in the oxygen that needs to be there and everything. So hexane part of hexanoate tells me on the carboxylic acid side, which is the base of the name, right, is the carboxylic acid side, I need 6 carbons. And the way I oriented mine here, my carboxylic acid side is to the left there. And I'm going to actually redraw it a little bit down to give me a little bit more room so I don't run out of too much room here. And again, carboxylic acid going that way. Now, the important thing to remember, though, when you are adding the 6 carbons to the left, there is, I already have a carbon, right? So I got to take that one into account there to my left. So you don't want to add an additional 6, otherwise you will end up with 7 carbons, right? Which is too many. So because you kind of started with the functional group, you already got a carbon hanging out there on the left, where the carboxylic acid. So really in this case, I just need to add 5 more to give me my, I moved and I still ran out, but we'll do our best there. So I'm gonna add 5 more. It gives me a grand total of 6 heading in that direction. And we got 1, 2, 3, 4, 5, 6. That takes care of really this part. And now propyl is the alcohol part, which should be heading in this direction. And that's going to be our alcohol part. And that is 3 carbons. And in this case, I don't have any carbons on that side. So I'm just going to add my 3 and I'll jump over the other side there. Now at that point, just like anything else we draw, we're just going to put our hydrogens in. And we're going to need 3 there. We're going to need 2 there. Going to need 2 there. We obviously will need 2 there. Actually, I'm going to, we'll do it. We'll squeeze it in here. We need 2 there. We need 2 there. We need 2 there. And at the end, we need 3 hydrogens there. So we should end up with CH3, CH2, 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 carbon oxygen double bond, O, CH2, CH2, and CH3. And she looks something like that right there, yeah? So again, kind of starting with the functional group sometimes is helpful. Even if you're going to do sort of like a line structure, you may also kind of want to start with the functional group. And that would maybe be something like coming down here, and then you would have that, right? And that would be sort of your functional group. And you could kind of do the same thing. You have one carbon up there, 2, 3, 4, 5, and 6. And over here, 1, 2, and 3. You could kind of put it in there in that direction as well. Any questions on that one there? Going to kind of work the same thing on this one. O8 tells me it's an ester. So again, I'm going to start with the kind of functional part of it just to orient everybody. And again, if it helps, you can put the line there. And that's going to be my carboxylic acid side, which will need 5 carbons total. Again, I already have one. So only 4 are going to be added to that one for a grand total of 5. And going the other way is going to be my alcohol part, and that's 4 carbons based off of butane, 1, 2, 3, and 4. And at this point, we're just going to kind of fill in some hydrogens, 3 there, 2 there, 2 there, 2 there. Obviously, nothing going on here in terms of hydrogen. And we're going to need 2 there, 2 there, 2 there, and 3 at the end. And again, I'm just going to redraw it here. I'll go underneath maybe. We'll go CH3, CH2, 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 carbon, oxygen, double bond, oxygen, CH2, 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 and CH3. Didn't get any better redrawing it, but did our best there. Any questions on that one there? Again, same idea. If you're going to do line structure, you can kind of just start with the functional group looking like this. And again, we got 1 carbon up on top, and we're going to go 2, 3, 4, and 5. And here, remember, this is going to be our first carbon on this side. So that's a 1, 2, 3, and 4 going in that direction. Any questions on drawing them there? So kind of like with the ethers, where you kind of start with the oxygen in the middle, kind of do both sides. That's a good approach with these as well, and leave yourself enough room to go each way there without running out. Any questions on that there? All right, so as I mentioned earlier, they are responsible esters for a lot of sort of smells and fragrances are due to it. And again, here's a table from your book with some of that. You can see here propyl ethanoate is responsible for sort of pears. Pentyl ethanoate, again, bananas, oranges, octyl ethanoate. And ethyl butanoate, pineapples, and apricots. And again, on each of these, if we were going to name it, we're just going to break them all right there at the single bonded oxygen. And again, always towards the double bonded is going to be our carboxylic acid and our alcohol side. This is also something that we talked about, I think, last time, but just to reiterate, as we can see here at the very top one with the propyl ethanoate, in this case, when we're naming esters, we're not necessarily looking for the longest carbon chain as the base of the name. So as you can see here, the base of the name actually has less carbons than the alcohol part, and that does happen in this case, and that's okay. But we're just looking for that sort of connection between the carboxylic acids and the alcohol. Okay, so looking at this, again, in this case, going backwards, we see oic acid. So again, not an ester in this case. This is going to be a carboxylic acid. So butane is 4 carbons. And once again, you do need the carboxylic acid group there, and you can put it at either end. I'm going to put it over here. And once again, you can't put it on that other side. But because I put mine over here, that would be carbon number 1 for me. And again, if you put it on the other side, your carbon number 1 would be on the other side. That takes care of pretty much of all that. So basically, I just need to go carbon number 3 for me, which would be right about here, and put a bromine, as again, that's carbon number 1. And now we could add our hydrogen. So I need 2 there, I need 1 there, and I need 3 there. Yeah. Any questions on that one there? That's obviously the condensed form. Again, you can kind of do the same thing there. You can start it with your functional group if you want to do line structure. Again, that's our COH. And then obviously here we're going to go one carbon up on top, 2, 3, and 4. And then over here would be my bromine, as that's carbon number 1 for me. Coming down here, we have O8, which tells us it's an ester. So again, I'm going to start with the ester group as to draw this. And again, I'm going to split it right there. And towards the double bond is going to be my carboxylic acid, which is based on the base of the name. So that's propane. So that's 3 carbons. Remembering I already have a carbon. So that's going to be 2, and that's going to be 3. Other way is the ethyl group, which is the alcohol way. And that's going to be a 1 and a 2 carbon. And at this point, we're just going to fill in some hydrogens. So 3 there, 2 there, 2 there, and 3 there in that case. And again, as we just mentioned a second ago, if you want to kind of do line structure, again, you can start with that functional group. And again, do your propane, which would be 1, 2, 3. And on the other side, ethyl, remember 1 starting here and then 2 starting there, yeah, or ending there. Any questions on drawing those there? Okay, the next thing we're going to talk about is a couple reactions that esters undergo, and they undergo what are referred to as hydrolysis reactions. And hydrolysis reactions basically means water oftentimes is involved. And basically, what's going to happen in certain cases is you're just going to get back the parts of the ester. So you'll get back the carboxylic acid and you'll get back the alcohol part. And in another case of a hydrolysis reaction, you'll get back only the alcohol and part of the carboxylic acid. So let's take a look at this here. In the acid hydrolysis, and maybe I'll redraw this one up on top here. And we're going to add water. And again, you may see this up on the arrow. That means you're adding heat. And this H plus just means an acid is being used as a catalyst. Hence why it's called an acid hydrolysis, because we have the acid present. So what's going to happen in this case is pretty straightforward. When you do the acid hydrolysis with water, you pretty much just get back everything that it came from. So you get back to 2 parts of your carboxylic acid. So all you have to do is, again, to keep it simple for us, you could just always on these esters, just draw a line there. And again, we know that if we go towards the double bond, that's our carboxylic acid. If we go towards the other way, the single bond, that's our alcohol. And that's really how I would just separate it out. And that's what's going to really happen here. We're just going to break it apart. So like the esterification reaction puts it together to make the ester. This sort of acid hydrolysis basically breaks it apart and back to originally. So if you remember, when we make it, we take water out. So in this case, we're throwing the water back in and we're going to basically break it back apart. So what you have to do is basically just draw the 2 parts that you broke it. There we got one there, which is our carboxylic acid. And this is the other part, which is our alcohol part, right? And we're basically just going to build out both of those things with water as our sort of pieces, if you will. So in order for our carboxylic acid part to become a carboxylic acid, it's going to need the OH. So we'll pop the OH on there. And now we have the full carboxylic acid back. That leaves us 1 hydrogen left there in water, which is great because what I'm missing there for my alcohol is a hydrogen. So I'm just going to pop a hydrogen on there. And now I have, again, both parts that make up the ester. I got the carboxylic acid part completed and the alcohol part completed as well. Again, just basically breaking apart how we name it, where we put that line between the carbon-oxygen single bond, break off the pieces, and rebuild basically both parts of that, the carboxylic acid and the alcohol. Any questions on that there? Now, the base hydrolysis is a little different because we're not really using water. We're using a strong base like sodium hydroxide or something like that. So because we're not using water, you can think of it this way. Water has 2 hydrogens and an oxygen. Here we're using a strong base, which has hydroxide, which is only one oxygen and one hydrogen. So we're kind of short the last hydrogen to get back everything originally that was there. So in this particular case, we actually don't get back everything that was there originally, but we do get back for sure the alcohol part. So we do get the alcohol part back completed, but we end up with really a salt for the carboxylic acid parts. So this is what sometimes referred to as a saponification reaction. That's a fancy way of saying how soap's made, basically. So this is basically how soap's made with really long chain carbons and stuff like that, is through this reaction. So what happens again, if we kind of look at this here, and the way you can kind of tell is the difference between, say, the acid hydrolysis and the base hydrolysis is we have here again a strong base involved. And that's going to tell you it's going to do really the base hydrolysis here. We also have some heat there. Now, really, it still really works kind of the same way. We're again going to break this guy up at the exact location. It's just, that's where we're going to basically break it up. And when we do so, we will get our two parts like we had on the acid one. We'll get this part here, and we'll basically get this part here. Once again, as I mentioned before, the only thing that gets completed perfectly here is not the carboxylic acid part, but the alcohol. So we do get the alcohol back completed. So once again, we're going to kind of pick some parts off of the sodium hydroxide here. So in order to get our alcohol back completed, we're going to have to borrow the hydrogen essentially, and that's going to kind of complete our alcohol. Now you can see when we come back to our carboxylic acid, we're kind of missing a hydrogen. We have an oxygen, but we don't really have a hydrogen there to get back to the carboxylic acid. So the only thing that's going to add on here is the oxygen. And that's actually going to be an oxygen really with a negative charge because, as we know, sodium is a positive one charge. And we will have a sodium hanging out there, which is sometimes written right next to it. And this makes not a carboxylic acid, but this is a salt of a carboxylic acid. And so in the base hydrolysis, we get only the alcohol back completed, and we get basically a salt version of the carboxylic acid, which is essentially the carboxylic acid minus the hydrogen at the end. And it has that oxygen ends up with a negative charge, is basically what you get there. Why this is called the saponification reaction is if you do this with a really long chain ester, in a sense, and you do this reaction with, say, sodium hydroxide, it will again break apart right there, and what you'll be left with, it's a really badly drawn thing, but you'll be left with something that looks like this. And, even have a sodium here. And this is basically soap. It has two parts soap. It has a non-polar part. All that is all carbons, right? And hydrogens, all non-polar all the way through there. And it has this front part, which is a polar part. And that's the sort of the ionic part of it, which is that guy with the charges. And that works really well as a soap because dirt is typically non-polar. And what happens when you put soap on is the non-polar part of soap will actually be soluble and mix really well with dirt. And what happens is it creates this micelle around the dirt. And what it ends up doing is aligning that carboxylic salt side outward. And that's really good because trapped in the middle of all those soap molecules is your non-polar dirt. On the outside is all the polar part of soap, which is really good because typically when you use soap, you usually follow it up with water, right? And water is polar. Like dissolves like. So when you wash with water, it's all cool. I'm going to be very attracted to that part of soap. And out goes the dirt with your soap, right? And you're clean and all that good stuff. Good thing to know how soap works, I suppose, yes. And it's basically this reaction with really long chain We'll talk about later in a later chapter. Fatty acids will make this soap. And it's usually really long chains of carbon on that non-polar part is what makes up soap. Any questions on that there? All right, so to review, acid hydrolysis, get both parts of the ester back completed just like it started. Base part, because we're not really using water, we're using a strong base, we actually only get the alcohol back, and we almost get back the carboxylic acid, but we're missing that hydrogen, which makes it, again, a salt at that point. So if we take a look at this guy here and see sort of what we get, if we started with methyl ethanoate, again here, O8 is an ester, so we're going to start with our ester group. And ethane is 2 carbons. So we'll end up with this as we go towards our carboxylic acid side. And methyl is our alcohol side. And we'll put a 1 carbon group. And here we're going to do water, heat, and an acid catalyst. So this is going to be our acid hydrolysis here. And remember, again, the acid hydrolysis is the one where you do get back everything. So that vertical line that we use a lot here with the esters, it's helpful in this part too. Again, that is where you can just break that guy apart into the 2 pieces. And once again, nothing else is changing, so we're just going to copy exactly what we got going over here. We're going to copy our carboxylic acid side, and we're going to copy our alcohol side, which is over here. And we'll get this. And really all you have to remember is if this is sort of the acid hydrolysis is I get everybody back exactly the way it started. And that means I'm just going to build out both of these things. So really all I'm missing here for my carboxylic acid is the OH. And over here I'm missing the H. And now again, I got back completed the alcohol and the carboxylic acid. So again, because we're using water. So if you use water in this reaction, you get back both parts. Any questions on that there? Now, if we did this one, which is KOH, that again is a strong base like sodium hydroxide and heat. We're going to start with our same ester. And once again, we're going to orient ourselves here by just kind of putting that vertical line. And here we're going to do KOH here. Once again, we're going to break this guy off into its parts, its alcohol part and its carboxylic acid part. So we'll just end up with our carboxylic acid part. And we will get our alcohol part here. Remember now, we don't have water here, so we don't have enough, if you want to think about it, letters to build everything back. But again, here on this one, we are going to get the alcohol back completed. So we are going to borrow, if you want to think about it, not exactly properly how this works, but we'll just think about it this way. We're going to borrow the H off of there, and that's going to complete our alcohol. And what's left is going to make that salt. So if you think about what we just talked about with soap, right? The carboxylic acid side is what makes the soap part of it. And that's going to be basically this guy. Just really get an oxygen with a -1 charge. The potassium here will be attracted to that, so you'll have the potassium kind of hanging out over there. And that's really a salt, right? An ionic compound. And that is what we're going to get here again, the salt of a carboxylic acid on the base hydrolysis. Any questions on that one there so far? All right, into our home stretch here of organicness. Down to the final 2. We're going to now talk about some organic compounds that contain nitrogen. So these are going to be nitrogen-containing compounds. The first one we're going to talk about are amines. And amines are really based off of ammonia. So if you remember, ammonia looks like this. So that's ammonia. And amines have the functional group basically of a nitrogen and some hydrogens attached to it. And that's the functional group of an amine. And as you can see here, got kind of those amine groups sort of happening. Now, amines, again, like I said, are basically ammonia derivatives. They're also fairly basic in a lot of cases, in which we basically have one or more sort of hydrogens attached to that nitrogen. And in this particular case, we are going to sort of name amines very similar to sort of how we name ethers. We're going to go with kind of the common way of naming it. But here's our ammonia, not ammonia, our amine, our nitrogen group. And in this case, we actually have three sort of groups attached to it. And we have this group here, and that carbon group there. Here we have a nitrogen, and what's attached to it is a benzene ring. And here we have our amine group. And again, we have a one carbon group there and one carbon group there. Now, basically, an amine will have this nitrogen and hydrogen set up. And by the way, not usually drawn, but there are some lone pairs there on the nitrogen. But again, usually not sort of put there. And once again, this is usually attached to some type of carbon group on this side. And every time we sort of put a carbon group on the nitrogen, we do lose the hydrogen. As you can see here, uh, no carbon group attached to the nitrogen. We have two hydrogens. Uh, Two carbon groups attached to the nitrogen. We have only one hydrogen, and three carbon groups attached to the nitrogen. No hydrogen. So if you got just one carbon group attached to the nitrogen, we'll have a nitrogen that has two hydrogens. If you have two carbon groups attached to the nitrogen in an amine, you will have one hydrogen attached to that nitrogen. And if you have three carbon groups attached to that nitrogen, you'll have no hydrogen. So this is sort of the starting point of amines with in terms of hydrogens attached to the nitrogen. And every time we kind of put a carbon group on there, we're kind of taking a hydrogen off and kind of putting the carbon group in that location. Now, just like alcohols and carbons, we could also classify our amines as primary, secondary, or tertiary. And it really does work the same way here in a sense. We are going to look at our functional group, which really is the nitrogen in this case. So we're going to take a look at the nitrogen and basically just see how many carbons are attached to the nitrogen. In this case, there's just one, and this would be a primary amine. If we take our nitrogen, and again, like I said, there are these dots that sometimes are not drawn on the nitrogen. We'll pop those dots on there this time. And we got something like this. And again, you can see we put one extra carbon group on. We lost the hydrogen from the guy over here. And now attached to this nitrogen, one carbon, two carbons. This is going to be a secondary amine. And just like the others, we can also have a tertiary amine where we kind of again replace that last hydrogen with a carbon group. And again, here we have attached to this nitrogen 1, 2, and 3. This would be a tertiary amine. So kind of like alcohols, kind of like carbons, we could also classify these guys as primary, secondary, or tertiary. And in this case, what we're looking for is the nitrogen. And again, how many carbons are directly attached to the nitrogen? Any questions on that there? So if we go back here, this would be primary, secondary, tertiary. This one would be how many carbons are directly attached to the nitrogen? There is just one. It's this one right here on the benzene ring. So this is a primary. This guy over here would be it would be a tertiary as it has one carbon, two carbons, and three carbons. And then obviously this guy down here would be a secondary. One carbon, two carbons would be a secondary on that one there. Yeah. Now, as I mentioned before, in terms of naming, we are going to take a more sort of common name approach with amines. So just like we did with ethers, where we took the common name, you could kind of do the same sort of move. If you remember with the ethers, we kind of put a box around the oxygen and then kind of identified the groups that were kind of to the left and the right of the oxygen. You could do basically the same thing here. You could put a little box around the nitrogen and identify the carbon groups that are there. And we are going to name the carbon groups as groups basically. So one carbon group would be methyl, and then we simply just put amine at the end. So this would be methylamine. Here, if we isolate our nitrogen, that is a methyl group, that is a methyl group. So again, we have two methyl groups, so that's going to give us a dimethyl. And we're just going to put amine at the end of it. And here again, if we isolate on our tertiary amine, our nitrogen, we got 1, 2, and actually 3 methyl groups and 3 prefixes tri. So this would be trimethyl. And once again, here we're just going to put amine at the end of it. So naming these amines, basically we're going to kind of name them common name and kind of go by the groups that are attached to the nitrogen. Just like normal, if there were different groups, we would go alphabetical order for the groups and regardless of prefix. So we wouldn't look at prefix, so we go alphabetical order for the groups and just put amine at the end of the name. And that's what you can see here. Again, our ethylamine. We go to our nitrogen here, and we got a 2 carbon group, gives us our ethylamine. There was our dimethylamine. And here we have an ethyl group and 2 methyl groups. So once again, that's going to be ethyl dimethylamine, alphabetical order. Once again, not looking at the prefix, so we're comparing the E to the M here, not the di part of the name. So we don't look at the prefix alphabetical, and that's why it goes ethyl first in that case and dimethyl second in that case by the comparison of these 2 letters here. Any questions on that there? Yeah. You would not. So this is more common way of naming. So you don't have to put numbers or anything like that. We're just gonna. It's very similar to the ether type of naming. The IUPAC way of naming is a little bit crazy-ish on these guys. So there is some numbers, some weird oxys and stuff like that you got to put in there. And so on this you don't. But because the idea here is we're basically naming the groups that are attached to nitrogen. So we usually will use numbers only when things are attached to a big carbon chain. So here, because they're attached to nitrogen, we actually don't use numbers, and it's just assumed where they're attached to that based on the amine part of it. Other questions? All right, so once you identify these, why don't you also just identify these as primary or secondary? It is a primary. Looking at the nitrogen, and again, carbon directly attached to it's only 1, so that would be a primary. Guy on B is a tertiary, 1, 2, and 3. And the one I drew it is a secondary. Here's our nitrogen, carbon there, and carbon there would be, again, a secondary in this case, yeah. Any questions on those there? Okay. Now, this can happen in certain cases, and you may see this, and I think your book might restrict it to just say aromatic benzene sort of amines, but it can actually be in some of the names for uh, non-benzene type of amines. Remember that if we do have a benzene ring attached to really an amine group here, that is that historical name that we saw when we talked about benzene in the 11, I think it was maybe. That is what is known as aniline. Now, in this particular case, we would name this as aniline, which is this guy here. And we do have a bromine group there, a bromo group. Remember where this functional group is at the ring is going to be carbon number 1 where the nitrogen is. That'll be carbon 2, 3, and 4. It really doesn't matter which way you go. It's going to end up at 4 no matter which way you kind of go. And in this case, that is how we get 4-bromo aniline. Now, when we look at this guy here, we also have aniline, which is basically this part here. But we also have something that is not a hydrogen because obviously the H is not drawn there, so that is just a line, and that is a methyl group. Now, to sort of an earlier question that was just asked, when we have a group that's attached to carbons, we usually will use numbers to indicate where on the carbon chain it is located. In the case of amines, even amides, which are also nitrogen containing, in this case, our methyl group is not attached to a carbon ring or the longest carbon ring. It's actually attached to the nitrogen. And that is why there is actually an N here in place of the number. The N indicates that that methyl group is actually attached to the nitrogen and not part of any type of carbon ring. And that is where the N methyl comes from. It's basically saying go to the nitrogen, you'll have a methyl group hanging out there. And then the aniline is the rest of the part of it. So you will sometimes see that N used kind of very much like a number is used with a carbon chain. Uh, and even, by the way, if we had something, say, like this, now, let's just say before we get to that guy, we had something like this. Just do something like that. So here, right, if we were just to look at this alkane and we were looking at our longest carbon chain, we'd have 1, 2, 3, 4, and 5. That's going to be pentane, right? And in this case, there's a methyl group there and a methyl group there, and that would be at carbon number 2, right? And we would have to give the number not once, but give it twice, right? Like a 2, 2, and then obviously here a little dimethyl, right? Pentane. Now, when you end up with two groups that are attached to your, say, aniline here, and they're actually attached, as you can see here, to the nitrogen. These are each methyl groups. That's a methyl group. And they're both, once again, attached to that nitrogen rather than carbon. Just like we give the number twice, we would also here do the N twice. So that would be NN, indicating that both groups are attached to the nitrogen. And this then would be a dimethyl, no, I could write dimethyl, and we would do aniline in this case as well. So just like we kind of use sometimes numbers and they're separated by a comma, if you have two groups that are attached to the nitrogen in an amine, we can use N comma N to indicate again that they are both attached to the nitrogen. Any questions on that there? And in the sort of more of the formal name, we'll sometimes see that used a little bit more. But here in your book, I think you'll kind of be restricted to kind of seeing it with the sort of aniline with the benzene ring and the amine. Any questions on that there? All right, so why don't you give these guys a name? Why don't you also draw? Why don't you draw? Let's see here. Let's do ethyl propylamine. Let's do N-butyl aniline. All right, so why don't you draw those two along with name the others? Okay, let's take a look. So again, we're going to start here with the nitrogen. We're going to go common name and just kind of identify what we got going on. So I got a two carbon group there and a second two carbon group over there. So that's two ethyl groups. So that's definitely going to have a diethyl component happening. I have obviously a one carbon group, which is going to be a methyl. And again, we're going to go alphabetical order. So we are comparing the E here to the M. So we'll go diethyl, methyl. And again, we're just going to put amine at the end of the name there. Any questions on that there? Coming here again, we got our benzene ring with our amine group on it, so that's going to have that historical name there of aniline. So again, our aniline is sort of this part of it. That's going to be the base of our name. We do have attached here a two carbon group, which is going to be an ethyl. And once again, in this situation, the ethyl group is not attached to a carbon, but it is attached to a nitrogen. So that's going to be an N-ethyl aniline in this case. Again, indicating that the group there is attached to the nitrogen. Yeah. Any questions on that there? Yeah. For which one now? Trimethyl for A, is that what you're asking? It would be wrong because each of these groups are two carbon groups, so each of these are ethyl groups. In order for it to be trimethyl, you would have just basically CH3 all around the nitrogen there on the three sides. Yeah. Other questions? Yeah. So remember here, when you're kind of counting the groups, it's kind of like what we do with ethers, where you just circle the box the oxygen and then count the groups. Here, you just want to box the nitrogen. The carbons here are not really a part of the functional group because the functional group is the nitrogen with the two hydrogens. So that's the functional group. So any carbon attached, in this case, you can think of it as a group. Yeah. Other questions? Yeah. Say it one more time. Yeah. Yeah, it's this side over here. Yeah. So really aniline is this, is a benzene ring basically with an NH2 up on top. And every time you put a carbon group onto the nitrogen, you lose a hydrogen. So we have this one carbon group here, so that's why we're just left with one hydrogen at that point. And that part of it there, what's left is basically the aniline part. Other questions? All right, let's draw a couple of these here. I think probably could just steal it just for you there, but we'll start again. All right. So kind of like what we talked about with ethers, once again here with the amine, I would actually just start with the nitrogen and just kind of work off of that since we kind of have the common names. So I have an amine, I know that's a nitrogen basically, and now basically I just have groups on whatever side of the nitrogen you want to put them. It doesn't really matter, to be truthfully honest with you, which side you put it, as long as it's attached to the nitrogen. So propyl is three carbons, so we'll just do 1, 2, and 3. And ethyl is two carbons. And like I said, it doesn't really matter sort of which side you put those groups. They can't go on the same side. They got to go on obviously on different sides of the nitrogen. And at this point, we can put our hydrogens in, and we need three there. We need two there. We need two there. We need two there. And we need three here. Now, there is one thing still missing, which is once again, the functional group of the amine is this. And in this particular case, we have one carbon group attached, and we have another carbon group attached, which takes out a hydrogen, and the nitrogen actually still has one hydrogen there. Just so you know it, again, it completes its octet, sometimes not drawn in, but there are those, again, non-bonding electrons there that gives nitrogen its 8 electrons that it needs around there and stuff like that. So remember that you do have to kind of subtract off a hydrogen for every sort of carbon group that's there, but you are only starting with two hydrogens, and it's implied that you already have one carbon group to begin with those two hydrogens. So if you have two carbon groups, you got to get rid of one hydrogen. Use the right finger there. If you have three, you got to get rid of the last hydrogen and stuff like that. Any questions on that? And that's what we see here. This guy started with two hydrogens with the one carbon group, but since it has an additional two, there goes the other two hydrogens. And again, that's why there's no hydrogen on that nitrogen, because technically there is the two lone pairs kind of hanging out there on that spot. Coming here to aniline, which again is our benzene ring. with our nitrogen. And same idea here, N-butyl means that attached to the nitrogen is a 4-carbon group. And again, here we'll put in our hydrogens. We need 3, 2, 2, and 2. Once again, here, does the nitrogen need a hydrogen? It does. It needs one more hydrogen. Again, if you want, you can put the dots and just count up the bonds, right? And it should have like, 8 electrons. So if it's missing, just throw a hydrogen on there and you'll be good. And it'll look something like that. Yeah. Any questions on naming or drawing those guys there? Okay. All right, so as you can see here, we could also do this in line formula as well. You do need to write the nitrogen in. Otherwise, if you don't, it's just going to be assumed to be a carbon. If you kind of just, you just do that, that's obviously going to be a carbon. So you do necessarily has to write the nitrogen in. And usually we do write the hydrogen as well, just to indicate how many hydrogens there are as well with that nitrogen. And again, here we have our primary at the end, our secondary, which has 1 hydrogen left, and our tertiary here, which again has no hydrogens left because it has too many carbons at that point. Now, in terms of solubility with amines, primary and secondary amines that have less than 6 carbons, they typically are going to be soluble in water, and that is because they can hydrogen bond with water. And tertiary amines, though, can form hydrogen bonds only with water molecules. Um, they cannot hydrogen bond themselves because they're missing a hydrogen. But they still have a nitrogen that can interact with the hydrogen from water, so they can do that move right there. But they cannot hydrogen bond. The primary and secondary amines, because they have, that's our primary, and our secondary looks something like this. Will be our secondary. Remember, in order to be able to hydrogen bond, you need a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine. So these guys have that ability to do so because they have a nitrogen attached to those hydrogens. But again, when we get to our tertiary amine, it does not have any hydrogens itself, so it can't hydrogen bond, but it can interact with water through there and make a bond between hydrogen and nitrogen with water, so it can still be soluble. So much like most organic compounds, kind of less carbons are best for solubility. Again, you get up for most things in that 4, 5, 6 or more carbons. You're going to really see solubility in water start to decrease because it's not going to be able to hydrogen bond as well. So primary means it can form hydrogen bonds more than secondary because it has 2 hydrogens versus 1. And tertiary, obviously, like I said, cannot hydrogen bond on the nitrogen, but can again form hydrogen bonds with water. Are alcohols as well. And again, it could do something like this, where we can get some bonding happening here between the nitrogen and the hydrogen. So in amines with more than 6 carbons atoms, the effective hydrogen bond is diminished, and the nonpolar part really kind of takes over and decreases the solubility. It again is sort of what we talked about previously when you get a lot of carbons kind of hanging out all over the place. This is what is sometimes referred to again as steric hindrance, which is a fancy way of saying it's just too hard for the water to get in there with all these big nonpolar things kind of hanging out there. So even though it technically has the ability to do so, these kind of big nonpolar parts of the molecule get in the way of that interaction from happening, rather than if you just had a nice small amine such as this, you know, this guy is relatively small, so water, again, is not going to have necessarily a very hard time to get in there and interact with it. Rather than here, you can see there's just a lot of stuff it's got to try to get around to interact. And you have a lot more non-polar part of this molecule than you do, say, with the one I drew there up on top, and that's not. Okay, let's take a look at the first one. So the first one is a primary amine, right? not too big of a nonpolar side, right? Less than 6. So we should expect this to be soluble in water. By the way, solubility in water is all about hydrogen, so it should have the ability to hydrogen bond there. This is a secondary amine. Also should be soluble in water. Again, not too big of a nonpolar part sort of happening. So again, should still have the ability to do some hydrogen bonding. This is a throwback from the past. This is an alkane, yeah. Way back there, we started our organic journey. Yeah. That is nonpolar all over, right? Which definitely means it should not be soluble in water, right? Like dissolves like. So this should not be this soluble in water. Any questions on that there? All right. Now, amines, because they are really based off of ammonia, and ammonia is a weak base, they basically will act as a base with water. So when an amine reacts with water, it basically will react as a base. It will react as a Bronsted-Lowry base, like we talked about in the acid-base chapter, which means it will accept an H plus from the water. So if we take a look at this simple methylamine here, and water, what's going to happen is this is going to act as our base or Bronsted base. This is going to act as our Bronsted acid. Acid donates an H plus over. And in this case, we're going to gain the hydrogen. And as we talked about in that acid chapter, remember that it is not just the hydrogen that is gained, but also the charge changes, right? So it gains something that is positive. So it becomes one more positive than where it started. It started neutral, so it became one more positive. By the way, when water loses the H plus, it is left as OH minus. This is why it is considered a base. It has the ability to produce hydroxide in solution, just like ammonia can. And it is a weak base. Most of these guys are pretty much a lot of what the weak bases are these amines. And they can basically just do like a nice old Bronsted-Lowry sort of accept an H plus from something like water that would act as the acid in this case. Any questions on that there? Now, we're not going to worry about salts. Definitely not going to worry about salts. But some of the ammonium salts are used, for example, in medications. Like we see Benadryl there. We do have this ammonium salt. It's basically an amine that has sort of a ionic compound with it, like a chloride. Some narcotics like cocaine also have that sort of group as well, that amine group happening here. And things like nicotine here. Also, again, we have our amine sort of group happening here. And our friend caffeine as well. We've got our amine group happening over here as well. Morphine as well. We just see our amine group. All right. So why don't you draw each of these here and see what you come up with. Okay, so since we're getting to the end, let's take a look. We got methylpropylamine. So once again, we're going to start with just the nitrogen here. And we're just going to kind of attach our groups to it. So propyl is propane, which is 3, 1, 2, and 3. Methyl is 1. And again, like I said before, you can kind of put it on either side you want. It doesn't really matter. As long as it's attached to the nitrogen here, we're going to add our hydrogen. So we need 3, 2, 2, and 3. And in this case, does my nitrogen need anything? It does need just one hydrogen. And again, you can put it on the top or bottom. It doesn't really matter on that case there. Yeah. Any questions on that one? Now we have 2-chloroaniline. So aniline, once again, is the benzene ring that has the amine group on it. So the chlorine here is attached to the nitrogen. It is not. Here we see a number, right? So the number indicates that it's actually attached to a carbon. So we always use numbers with carbons. So if it was attached to the nitrogen, it would say N, right, instead of the number. So remember that where the nitrogen is attached to ring will be carbon number 1. And since this is a benzene ring and it has those 3 double bonds, you could actually go either way on this case. You could go to the left, you could go to the right. I'm just going to go to the right and call that my number